Today is the first class on deep learning algorithm theory. Since it's the public version, I will try to make it more interesting and minimize boring formulas. And the more detailed and hardcore version will be updated in the paid course. I choose to start with the derivatives as the appetizer, from the first order to the fourth order derivatives, as derivatives provide the computational basis for optimizing loss function in deep learning. My personal favorite way to understand derivatives is through the geometric or physical interpretation. The first derivative corresponds to speed. The second derivative corresponds to acceleration, which is the change in speed. The third derivative corresponds to jerk, which is the rate of change in acceleration. And what is the fourth derivative? We can deduce it as the rate of change in jerk. It sounds like nesting dolls. Although the fourth derivative is not very relevant in current deep learning operations, it doesn't hurt to learn more. In physics, it is called drones. Let's start over by drawing a coordinate system with the x-axis representing time and the y-axis representing distance, assuming the car always moves in a straight line. We can see that the speed of the car is constantly changing along the curve. To obtain the speed at each moment, just draw a tangent line at that point. And the first derivative is exactly the slope of the tangent line. Different time points corresponding to different tangent slopes, and connecting all the results will give us the first derivative curve. Continuing to take derivatives, we'll get the second derivative curve, where we can see the accelerations change from positive to negative. Further differentiation yields the third derivative curve, which shows that the rate of change in acceleration is also not uniform. We can assume that the car undergoes sudden acceleration or braking, in which cases the absolute value of the third derivative will be large. From a physical perspective, the value of the third derivative can be an indicator of passenger comfort. A smaller absolute value indicates less impact felt by the passengers. In machine learning and deep learning, the loss function is used to measure the difference between predicted values and actual values, and continuously update parameters to minimize the loss function to be as close to zero as possible. So, how derivatives specifically help optimize the loss function, I will find an opportunity to elaborate on it later. Moving on to today's main topic, everything can be modeled. Before the advent of AI models, the ancient Greek philosopher and mathematicians Pythagoras proposed the famous theory always number. This is essentially the same as the idea that everything can be modeled. Taking the most explicable human issue of love as example, if I can convert the most irrational and chaotic problem of human love into an mathematical or modern problem, I indirectly prove that everything encountered by humans can be solved by mathematics or modeling. For instance, if you have a crush on someone and want to know if confessing will be successful or not, so you need to predict the outcome. How can you model it? First, define the output format. Let the mathematical function or model predict the result. Output 1 for success and 0 for failure, making it a binary classification task. If your capabilities are limited, you can set the variables to the minimum, selecting only the most critical ones such as intelligence, education, appearance, income level, yours and the other person's. And each of these variables can be further refined. If your capabilities are strong and you want the function or model to have more criteria for judgment, you can continue adding variables without limit, such as friendship situation, even as detailed as the number of childhood friends or friends in adulthood. Family backgrounds like parents' occupation, annual income, total assets, presence of domestic violence, etc. Personality traits, introverted or extroverted, susceptibility to environmental influences, self-confidence, impact on others, artistic cultivation, etc. Where the degree of scientific refinement of the variables are directly proportional to the model's performance. The following step is to select or design a mathematical function or model structure for modeling. You can even design just one simple linear or nonlinear function, but the predictive effect will be very poor. Even using the traditional machine learning models will not significantly improve the results. So it is advisable to employ the state-of-the-art deep learning neural network structures for the modeling. Neural networks also come in different types, with unit structure involving from convolutional neural networks and recurrent neural networks to self-attention. The complexity of the model structure is proportional to the model's performance. Then comes the data collecting stage. For this question, what kind of data do we need? If an algorithm engineer cannot come up with an answer within 2 minutes, then their problem-solving abilities are in question. We need a large number of data samples of successful and unsuccessful confessions, including the condition variables of the confessing parties. To ensure sample balance, it's best to have a ratio of 1:1 of successful and unsuccessful confession samples. Assuming we have already collected 1,000 successful confession samples and 1,000 unsuccessful ones, we can start training our models. Training on a small dataset has the benefit of avoiding spending too much time initially on verifying the effectiveness of the model, and then moving on to large datasets. Common evaluation metrics for binary classification models include accuracy, recall, and the balanced F1 score. Typically, a F1 score exceeding 95% indicates a good model, meaning enough for deployment in industries in most scenarios, while achieving over 95% is considered excellent. Even with current models like ChatGPT, you can inquire about love matters, but it lacks the specific ability to accurately predict the result for confession. The reason is that it is a general purpose conversational AI models, not specifically trained for love matters. Personally, due to my laziness, I am open to welcome others to implement my ideas, so we can have a love expert model to help modern individuals save time on emotional issues. Following this example, let's further consider training a model that can predict the happiness level of a couple after marriage. In this case, the output of the model changes to a multi-class with a range of -10 to 10, or regression model. But collecting the corresponding data sample could be challenging. We would need a large sample of married couples. And besides the conditional variables, we would need to assign a happiness score to each married couple, which is the data labeling process in machine learning and deep learning. We can assume happiness is entirely subjective, or can also include objective factors. We would need to design scientific weights and evaluation methods to calculate the comprehensive happiness score. Compared to the labeling of success or failure in confession, the cost of labeling post-marriage happiness will be higher. This is why in training of powerful AI models, the labeling process and sample quality are critical factors affecting the results. This concludes the content of the first theoretical class. Personally, I'm looking forward to the application of AI models in various rational and irrational fields, which is where AI models will surpass human intellect. Although deep learning was initially inspired by human brain neurons and developed neural networks based on that, it can be used for a variety of mundane issues that humans are not very interested in investigating. And it only takes a few hours training to achieve a godlike level in solving these problems. This will give humans more time to invest in pursuits they are truly interested in. Further differentiation of the third derivative curve, which shows that the rate of change. 其实我即兴的也可以，强迫症犯了，我就是要一字不差。Further differentiation of the third derivative curve, which shows that the rate of change in acceleration is also not uniform.